So hello everyone, welcome to today's Luohan webinar. My name is Jiewei Li, and I'm a moderator for today's session. I'm currently a PhD student at the School of Management at University College London. Today we are very happy to have Professor Agostino Capponi from Columbia University to share his research about graphic machine learning for asset pricing, traversing the supply chain and factors rule. Let me briefly introduce Professor Capponi at first. So Professor Capponi is currently a professor of industrial engineering and operations research at Columbia University. And also he is the director of the Center for Digital Finance and Technologies. Professor Capponi is also affiliated with the Data Science Institute at Columbia. Professor Capponi's research covers primarily critical areas, including market microstructure, financial technology, economic networks, and applications of machine learning in finance. Regarding today's session, we will have 1 hour. Professor Capponi will present his research in the beginning for about 15 minutes, followed by a 10-minute Q&A session. So for audience, if you have any clarification questions during the talk, please feel free to briefly unmute yourself to ask. If you have any other questions, we kindly ask you to reserve them for the Q&A session in the end. So without further ado, please join me in warmly welcome Professor Agostino for his presentation.
Thank you, Jiewei, and thanks for everybody for attending the seminar, the webinar. As Jiewei mentioned, please interrupt me anytime. I think it's great if we have a more interactive discussion rather than maybe asking the questions at the end. And yeah, I'm going to present a new paper that I've recently completed on the graph machine learning for asset pricing. And the objective is basically to integrate the supply chain graph into asset pricing models. Joint work with Jose Sidawi, a PhD student in the department, and Jiasheng Zhao, who was a postdoc here at Columbia. So let me start with a slide on motivation. The reason why we undertook this project is because we wanted to understand whether supply chain relationships can have an impact in determining how asset prices are formed. So what's the impact of supply chain information on firm returns? And of course, I mean, I don't think I have to convince you that this is important, especially in light of what we observed recently with COVID or the geopolitical and events that we have seen around the world. So this basically makes the strains or shock occurring on the supply chain even more important to understand their implication on asset prices. And despite all this, there is what we found is that there is no universal approach to account for supply chain data into those asset pricing models. And there are several reasons why this is difficult. First, if we think about linkage between firms, these are most likely commercial secrets. So some firms essentially establishing relationship with others, and you may not be, maybe you don't know that because they're not reported. As also, like some of the connections are missing. For example, like in the data set, you don't observe this connection, or they are endogenous, right? So firms decide to form relationship with others because they have strategic reasons to engage into such relationships. Of course, the relationships are dynamics in the sense that firms might have a relation, but then at either point in time, they might break this relationship. So there are linkages which are formed and removed at any point in time. And of course, the graph is very high dimensional. Think about having 1,000 firms, then you have 1,000 choices to possible links between firms, right? So that's like a very large and complex data set. And what we want to understand is how we can integrate this data set for asset pricing. And what we're going to do is we're going to propose a data-driven approach, what we call basically a methodology which looks at the data and try to construct asset pricing factors, which means factors that can contribute to determine the prices of firms, right? And there, when I say prices, I mean stock prices of firm. And we do so by combining in the appropriate way firm-specific information, let's say balance sheet data such as debt to asset ratio of the firm, or leverage of the firm, or size of the firm, with relationships that the firms have with others in the network, both direct and indirect relationships. And that's basically the main contribution of the paper, like to come up with this approach, and then, of course, to show how this approach works when we look at the real data. So let me just explain what is the supply chain graph and what type of data we are using. We are observing firm return. So these are like stock returns of firm, which I'm denoting by YIT. So this is the return of stock I at time T. And then for the same firm, we observe a rich set of firm characteristics. So the finance literature has identified a number of characteristics which could be useful to price stock, right? And we are basically taking into account, we are looking at all firm characteristics that have been identified in the finance literature, and we are using them to integrate this set with supply chain graphs. Now, the firm is represented as a node in the graph, and this node has two attributes. One is the return of the firm, or the return of the node I at time t, and the other is the value of the characteristic of firm I at time t. And then the graphs are essentially relationship between nodes. So, for example, if we look at Apple, Apple has its own stock return, and they have their own characteristics. And then Apple is sourcing some of the inputs that they need for production from other firms, and they are also delivering the goods and services that they produce to other firms, right? So that's basically, in a nutshell, what a node in the graph, how a node in the graph looks like. And on the other hand, like if I look at really the neighbors of Apple, then we suppose that we look at a very simplified stylized network where Apple is sourcing from Intel. So the Intel is selling all the chips and manufacturing components that Apple needs to produce, for example, the iPhone, and then Apple sells the iPhone to, let's say, Best Buy, the consumer electronic firm. Now, this is basically represented as a line graph if Apple only sources its input from Intel and only sells to Best Buy. And all these firms will have their own stock returns, and they will have their own characteristics. So that's basically an example of the Apple supply chain. Of course, supply chain is more complex because there is, Intel, for example, like may in turn have its own supplier, like in this case, CXMT. That's a company, that's Taiwanese manufacturing company, which sells like hardware, which is delivered then to Intel so that Intel can produce their own chips and semiconductors and sell them to Apple. And of course, Intel doesn't have to sell only to Apple. It can also sell to Microsoft, right? They sell to all firms which uses their processor, companies that produce like software systems. And then, of course, both Apple and Microsoft can sell their products to Best Buy. So in this case, the supply chain is more complex. And also I want to highlight that in the data, we are looking at firm returns and firm characteristics. But for some firms, for example, this CXMT, that's a company based in Taiwan, this is not traded in the main indices that we have. Well, there is no return of the stock because the stock is not traded, but still we can observe the characteristic of the firm, right? We can still observe, for example, their balance sheet information, we can still observe their profitability and so on. So that's basically in a nutshell what we do. And the objective here is to extract factors that predict both the Microsoft stock returns and the Apple stock returns co-movement, right? We want to take into account the fact that these two returns can co-move with each other because they have common supply chain relationships. And hopefully, ideally, this correlation will be captured by the supply chain graph. In fact, what I'm going to discuss in this paper is first the methodology to build factors from integrating characteristics with the supply chain graph. And then I'm going to use this to predict stock returns. But the first part of the talk, so the methodology to construct factors from firm characteristics integrated with the supply chain graph is very general. In principle, in theory, one could basically use this for other purposes. It doesn't have to be necessarily used to predict returns, right? So I think this is a very, in my view, an interesting methodology to just integrate less structured data, let's say supply chain graphs, with more numerical data, which are firm characteristics, and then use them to make inferences or to solve or predict other quantities of interest. Okay, good. And I also want to make a point that all our analysis should be taught as a conditional analysis. So in other words, we take the graph as given. We are not really looking at why the graph is the way it looks like. Why do we have this specific graph? Like, we take the graph as given, and then conditional on observing this graph, we try to understand what are the most relevant factors that can be constructed by integrating firm characteristics with stock returns and supply chain graphs. Okay, so two main questions that we are after. Like, first is, what is the incremental value of the supply chain graph in explaining firm level returns? So is there any value in using the supply chain graph to explain firm level returns, right? Or is it possible that perhaps the firm level returns are already explained by firm characteristics alone, and we don't need to take into account supply chain information? And the second question is whether we can provide a better approximation for the stochastic discount factor using the supply chain graph. So the stochastic discount factor is essentially the risk premium. So understanding what's the additional compensation that investors want or demand to bear the risk. And we want to see whether the supply chain graph can give us some additional information, independent information in a relation, on top of what is already captured by the firm characteristics alone. So the contributions, I think, are two. First, I think on the methodological side, as I mentioned, we first propose a graph learning approach, which is based on financial economic principles. And this first part, I think, in general, it's principle can be potentially also useful for solving other problems. Because we are interested in asset pricing, we are essentially extracting hidden asset pricing factor from the supply chain graph. So when I say latent, it means that these are not really directly observable, but they are hidden, and they should be. It's like you have to single out those factors by analyzing the supply chain graph. And this is different from handcrafting structural signals from graph. Like, we are not really directly constructing the signals ourselves. Say, okay, one signal should be, let's say, the centrality of the network. No, we are the centrality of the graph. No, we are trying to have the data speak and tell us what should be the real or the most relevant pricing factor here, as the pricing factor. The other is that we are tackling noisy, dynamic, and n-dimensional supply chain graph data, because, as I mentioned earlier, like, the supply chain graph is huge and it's very n-dimensional. It changed over time. Everything that we do is conditional. As I mentioned, it's conditional on the observed supply chain graph. And because this graph is changing dynamically, it provides some variation for us to analyze effects of graph structure, for example, centrality of firm or return. We can ask questions such as, okay, if I look at nodes of degree 1 or degree 2 or degree 3, so the higher is the degree, in principle, the higher is the degree centrality of the nodes, and therefore, is it true that this will have a higher impact on the returns of the firms? And in order to integrate this information from the supply chain into and combine them with firm characteristics, we are going to leverage message passing algorithms that essentially are well designed for graphs where there is a rich context. The context is essentially the node characteristics. And what we show is that this model is improving in terms of the pricing error over the traditional benchmark, for example, the Fama French 5 factor. So that's the classical asset pricing model in finance, where you assume that 5 factors, including the market cap of the stock, the index, the book to market ratio, and so on, they explain all the variation in the data cross-sectionally. And it also improves over another recently proposed methodology, which is called risk premium PCA. So that's basically a principal component analysis where you balance the mean with the covariance. Like, in the principal component analysis, you only look at covariance. With RPPCA, you look basically at first and the second moment. And we also identify some restructure in the supply chain data. In fact, we find that 5 factors are capturing over half of the out of sample Sharpe ratio gain. So if you look at the Sharpe ratio out of sample on top of what is already captured by the firm characteristics alone, you see that more than half of the remaining Sharpe ratio is captured by just 5 factors. So it's like a factor model for supply chain. Here we say, okay, instead of, it's like the Fama French 5, only look at firm characteristics. Here we say, if we additionally look at supply chain, it's enough to consider 5 extra factors if we want to capture more than half of the Sharpe ratio gain out of sample. And we are also showing that the size of the local subgraph matters, in the sense that it's not true that the more like higher order effects, the more like linkage you consider, if you look only at the neighbor or the neighbor of your neighbor and the neighbor of your neighbors and so on. So it's not true that the deeper you go into the network and the better is the asset pricing. There is a bias variance trade-off. So if you include like a very small subgraph of a node, so if you only look, let's say, the degree of node, the neighborhood of that node, or the neighbors and the second order neighbors, which means the nodes that are at distance 2 from the node that we are interested in, then perhaps this is not really capturing all the information that we want, and therefore there will be some bias. But if you keep increasing the hopes that you consider from the target firm, then you might introduce excessive variance, because maybe you are taking into account information coming from nodes which are far away, which is not really relevant. So this is basically more contributing to increasing the variance, and rather than like really improving the asset price prediction. Okay, there is a lot of literature on the topic. Of course, I mean, people have looked at supply chain graphs from different perspectives, like how supply chain shocks are impacting the performance of the firm. Then there are people, there is a separate branch of literature which looks at supply chain shock data and their connections to promising finance and economics. And recently, also some papers have looked at machine learning method for asset pricing data, but most of these papers don't take into account, actually all of these papers do not really look at the supply chain. They just try to understand how you can improve asset pricing model if you have like big data, which means essentially you have an incredible higher number of firm characteristics, and then let the machine pick the characteristics which are more predictive for the data. But again, ignoring the supply chain information in this case. So it's like bridging this paper, the literature in OM, where I think the focus has mostly been on understanding how supply chain supply chain shocks impact the network, at best taking into account just, let's say, neighborhood of size 1 of a node, and the literature in finance, which of course has grown a lot in the recent years to understand the role of nonlinearity and machine learning for asset pricing. Okay, so now going forward, I'm going to discuss the methodology. So let me introduce some notation first. I think YIT, as I mentioned earlier, is the return of stock I at time t. And here we're looking at returns of firms in different indices. We're looking at NYSE, NASDAQ, and the American Stock Exchange. So this is basically a very rich set of stocks, because it includes all the main, most legally traded stocks that we have. And we are going to also, for XIT, we are looking at 64 lagged firm characteristics. So we are taking this characteristic from a paper, Freiberg, Neuber, and Weber, which have constructed this firm characteristic and show that these are like the most significant for asset pricing. And these are lagged characteristics because when we look at the data, so why is the returns of the firms, these are, for example, available on a daily basis, right? You observe the stock returns, but if you look at the characteristics such as book to market ratio of a firm or debt, these are available, for example, every 3 months. So if we have to make an inference, let's say in February, we are not going to use the balance sheet data as of March. This balance sheet data released the first time in March, but we are going to use the one released in December. So that's why there is a lagged characteristics. We try to basically, we have a methodology to describe exactly what is the lag that we use for each characteristic that we have in the paper. And then we are also limited in a way in our data set from the SEC SFS 131 Act, which is one of the accounting standards determining the disclosure of firms. So this basically each firm is required to disclose all customers if they have a relation with them which is significant. So that means that each firm must disclose all their customers for which they have a number of sales which is larger than 10% of their entire sales. So in a way, if let's say Microsoft is selling to Best Buy and is selling like more than 10% of their entire sales to Best Buy, then you will see this edge appear in the graph. But if Microsoft is selling maybe to another smaller company and the amount that it's selling is less than 10%, you don't see this link in the graph. Okay, so that's basically, this is just a restriction that we have from our data set, which is sourced from CompuStat segment and CRISP. And then again, as I mentioned, like for the stock returns and XIT, we look at monthly data. So even if we have stock returns every day, we still look at the returns of the stock and the characteristics of the firm on a monthly level. And then for the supply chain graph, we only see this information every year. So every year we see what are the new links appearing in the graph, which links have been removed. And also we observe quantities traded within firms, but not always. So sometimes we also see the size of the trade. Some other times we don't see the size of the trade. As a result, we are not taking it. We are only looking at binary information. So whether there is an edge or there is no edge, we are not looking at the weight on that edge. And then we look at, we benchmark this model with a factor model, but without using the supply chain graph. For example, we want to see how does it compare to a simple FAMA French 5 model, where, again, you don't take into account any supply chain information, but you just regress stock returns on some firm characteristics, and also with the risk premium PCA that I mentioned earlier. And we extract factor from basically both firm characteristics and supply chain graph. And actually also what we do, we benchmark our methodology with supply chain graph, but without using the graph model. For example, like there is a paper by Agisha, Babic, Birge, and Wu that has looked at nearest neighbors. So essentially only consider the characteristics of your direct supplier and customer. So you don't look deeper into the network, but you take into account only the first order connection of a node. And I mean, what we do in contrast to them is basically looking at higher order relationships, not just at the direct neighbors, but also the neighbor of their neighbors. And we want to see whether or not these higher order relationships have a material impact on the stock returns, right? Because if not, then one could just go with a simpler nearest neighbor procedure. Okay, so first I want to mention, okay, how do we represent the supply chain graph? I think there is an effort to make in terms of how to best represent the network, because we have nodes, as I mentioned, which are the firms, and then we have linkages, which are the edge. So EIJT here is the link between firm I and firm J at time t. Okay, so now what we do, we associate each node with 64 characteristics, and also we have the returns. So now if you represent the graph as we do, then we have 64 plus 1 nodes. So that's the dimension of the graph, because we have the 64 characteristics plus, of course, the node itself, and then we have the edges. So the alternative, which is a bit, let's say, inefficient, is to store pair of firms. For example, we store I and J, and each I mean, I consists of stock returns and firm characteristics. So I consists of YIT and XIT. J consists also of stock return and firm characteristics, so YJT and XJT. And then this will lead to a naive representation, because in this case, we will have the dimension is equal to 2 times the 64 plus 1 times the number of edges. And of course, if you think that if the graph is reasonably dense, I mean, in general, the number of edges is usually larger than the number of nodes, right? At least if the graph is not really very, very sparse. And in fact, in the worst case, if you have, for example, pairwise relation between all nodes, which is, of course, not the case in the supply chain, but I'm just making an estimate of what would be the dimensional gap in the worst case, it will basically be scaling as the number of vertices to the power 2. So there is the representation we have is essentially efficient in terms of capturing the relationships, but in a parsimonious way. And the goal is, as I mentioned, capturing interaction in the supply chain, and we are going to use some nonlinear functions to integrate this to integrate the information coming from this interaction. And how it works, essentially, we will implement a message passing algorithm that propagate information through the supply chain graph. And in each layer of the network, we are going to update the firm characteristics by aggregating information from all its neighbors and combining with its own features. So each node is essentially taking all the information from their neighbors, which are, of course, information about the characteristics of their neighbors, and then they are integrating this information with their own features. And then we will predict the returns of the firm of the stock I based on this enriched feature set, right? Features that have been integrated, that have been enriched with information coming from the neighbors of the node. So you can think of this as a very nonlinear form of regression. You always combine firm characteristics, merging them, and then coming up with a new enriched feature set. And I will describe this in more detail in the rest of the talk. And the reason also why we use graph neural network, I mean, unlike traditional machine learning model, these are very well designed to solve problems in graph-based learning. So if we want to learn information from a network, that seems to be very promising and natural technique to use. And also it allows us to model like complex relationships efficiently in the supply chain. So now let me give you some intuition on how this message passing algorithm works. So the graph neural network is basically computing weighted nonlinear averages of firm characteristics in the following way. Suppose that we look at the left graph. Like in the left graph, I'm looking at an example of a supply chain graph. And let's say that 1 is the target firms. So now in the right panel here, I'm producing the GNN network corresponding to this graph. So if I look at a depth of the graph which is equal to 2, that means that I take into account the nodes that are a distance 1 from node 1, which is the target firm, and also the nodes that are a distance 2 from firm 1, which of course are node 5 which is, or equivalently, these are the nodes which are a distance 1 from the neighborhoods of node 1. So 2 and 4 are a distance 1 from node 1. And then I look at the neighbors of 2, and the neighbors of 2 are 1 and 3, which are a distance 1 from 2, and the neighbors of 4 are 1, 3, and 5, because they are a distance 1 from 4. So this will be a d equal to 2 network. So the depth in this of the graph neural network in this case will be equal to 2. And then what happens is that the node 1 and 3 will send a message to 2. And this message will be constructed using this GNN layer. The node 1, 3, and 5 will send their own messages to node 4, and node 4 will integrate these messages and update its own feature set. Then 2 and 4 will send this updated feature set to node 1, and node 1 will integrate this feature set with its own information. And after all this process is done, 1 will have constructed its own embedding. So embedding here, we mean the final feature set that has been constructed by taking into account all the information that has been passed from the nodes which are a distance 2 from the target firm 1. And
Hello.
yes.
Hi, Agostino. I have a question. So for clarification for now.
Sure.
So can you describe a little bit, maybe I missed it, what exactly is the data itself? So what exactly is this learning from, right?
Yeah.
And so when you're talking about the linkage message sent to each other, what exactly is the message? What are we kind of subtracting things from, you know?
Okay.
Can you explain a little bit?
Thank you so much for the question. Yeah, let me go back a few slides so that I start with your question about what is the data. So the data is for the message passing, what is relevant is this data set X. So X are firm characteristics. So these firm characteristics are let me show you what these characteristics look like. So this is well. So the let me see if I have information about that. Sorry, no. Yeah. So the firm characteristics are essentially the accounting information for the firm. So let's say that you look at in this case Apple, right? So Apple will have balance sheet information, right? You can look at the debt of Apple, you can look at the asset size of the firm, the asset size of Apple.
So it's like a lot of CompuStat stuff.
Yeah, CompuStat stuff, right? We are using CompuStat segment to construct these firm characteristics, right?
Sure.
That's good.
So
and
so what is the message that link to each other?
Yeah,
so
the message
so
that is that's a good question. So the message that we are linking, and that this is coming next, is essentially passing this X to each other. So one is let's say, suppose that we look at this network, one is going to pass their own characteristics to this GNN layer, 3 is passing its own characteristics to the GNN layer, and this GNN layer will weigh them properly and construct a new, let's say, higher level characteristics, which takes into account the contribution coming from characteristics from 1 and characteristics from 3. It will pass them to 2, and 2 will integrate this information with its own characteristics and then pass them to 1.
So let's say we have a concrete example. Let's say we have a firm of Apple.
Yeah.
Which kind of characteristic from other firm, whatever, or from other characters, can you give some
an example could be
how are they linked to each other?
Yeah. So I think if it's coming in the next slide, it's not like a concrete example, but I'm going to discuss how this message passing algorithm works. But essentially, think about Apple getting, for example, characteristic information from Microsoft and from another firm which produces semiconductors. So they will say, okay, if let's say Microsoft is large compared to the other firm, then I will weight Microsoft firm information more. But we don't have to impose this a priori. The neural network will decide how to construct this integrated characteristic.
So
and
basically,
then think about having a very simple case. You could regress. You could compute a weighted average of the characteristics of Microsoft and the other company, and then pass this weighted average to Apple. Right? You could do that. Here I'm saying instead
Sorry. So you don't tell the model who Apple is related to, right? It learns by itself. Is that am I correct?
I think whatever I observe, if I see that there is a link between Apple and Microsoft, then this message would be passed from Microsoft to Apple. Right? If there is no link between Microsoft and Apple, I will not observe this message. So the algorithm
when you say there's a link, you do mean there must be a certain pattern that the model will identify by itself.
A link,
you don't impose this.
No, a link. I mean that looking at the CRISP data set, right? CRISP, like, yes, you have that all firms are required to disclose business relationships with customers for which they have above 10% of the sales. So this is basically the graph that I observe based on the data. So if there is a relationship, then I will observe this link. If there is no relation between customers and buyers, then I don't observe this link. So I'm not imposing it a priori. It's basically, this is just, it's conditional analysis. Based on what I see, I take into account. So if in the next period this link disappears, you will not see this link anymore. Right. So you see the link with yeah, go ahead.
Let me reiterate. I'm trying to ask. So basically you use the CRISP data to identify the supply chain relations. Then you ask the model to apply its to judge the weights you should give to something. Is that correct?
Yeah, exactly. The model is deciding the weights that you should be given. Yeah.
Got it. Yeah.
Thank you.
Thank you. Go ahead, please.
Yeah, thank you. Okay, so let's, I think these are part of the answer to the question that Liao had. So they say that we denote this embedding as H. So let's say that this is the embedding that I'm constructing. So embedding is the updated characteristic, right? This updated feature that I described. So in each layer of the graph neural network, you have 3 steps. First, you calculate the message. So the message that J is sending to I in layer L, right, is equal to some nonlinear function, which I'm denoting by FMSG, which will be estimated from the model, which takes into account the embedding constructed by I at layer L-1, the embedding constructed by J at layer L-1, the characteristics of node I, and the characteristics of node J. And then we will compute this message. So as you see, the message that J is sending to I depends, of course, also on the characteristics of firm I and also on the embedding that firm I has. So then I will aggregate all these messages coming from its neighbors. NTI is the neighborhood of firm I at time t, so all the nodes that are connected to I at time t, and they will aggregate them using some function. So for example, this aggregation function could be the sum, could be the mean, could be the max, right? We will not really pick a specific function, but rather we will let the model decide which function to use. And then there will be an update step. So the update step will be combining all the messages that have been received with the node current features, and then it will produce a new updated feature. So you look at the current feature of node I at layer L-1, combined with the message computed by node I in the iteration L, and then this will compute the updated embedding. So these are the 3 steps. So what we need to do is to compute this FMSG, so the message calculation function, the aggregation function, and the updating function. And in the end, HID will be the final embedding. So this is the embedding taking into account the layer D of the network. And finally, what we do, we are going to regress we do a linear regression of the returns on these embeddings. So in a way, these embeddings, as I mentioned at the beginning of the talk, are integrating the firm characteristics, the firm own characteristic to supply chain graph, right? Because you are taking into account essentially all the relationships that firm I has, depending on the size, on the depth of the network, you can go further down and integrate more and more characteristics coming from the neighbors. And let me explain, okay, the role of D. So as I mentioned, D is equal to 1. It means that we only look at very local subgraphs. That means that you only capture immediate supply chain dependencies. You only look at the direct suppliers or the direct customer of a node, right? Because you only focus on the neighbors. So this is limiting scope to what we think is local risk, because if there is, let's say, if a node which is in your neighbor, for example, the node that a firm that you have a direct relationship with, going back to the example of Microsoft and Apple. So if Microsoft has some problem, right? So that means that this is reflected in their own balance sheet. Then this will be seen from Apple, because Apple is integrating the characteristics coming from Microsoft with its own characteristics. But if like a supplier to Microsoft, which is a node at distance 2 from Apple, is subject to some shocks, this will not be visible directly, right? At least it will not be visible from the supply chain. And this D equal to 1 is basically what is the focus of the previous literature, as I mentioned earlier, the paper that looks at direct neighbors. Then if you look at large D, that means that the model is learning from an expanded subgraph, right? That means that you are taking into account more neighbors, like second order, third order, fourth order relationship between suppliers and customers. So that means that you will be able to capture higher order disruption that are propagating through the supply chain graph, because you see really nodes which are distant from your from you. And of course, this will give you some more expressiveness, right? Because you are essentially, the model is more complex, so it's more expressive. It's capturing a richer set of features. But again, as I mentioned, you have to be careful with bias variance trade-off, which is what we find actually in the data. If you make D too large, then you are introducing noise, right? And in other words, there will be some information dilution effect, because you are taking into account information which is also coming from nodes which are far away from the target node. And this information, the nodes that are far away from the target node, are not really contributing much in terms of information for the current node. But on the other hand, if you select a D which is too small, then you might be introducing some biases, because you are omitting some complex relationships. And of course, if these too high, there are also additional problems. In addition to the information dilution effect, there is also like problem with estimation challenges. For example, there is vanishing gradient. So the gradient tends to be very small, very close to zero, because the model is like over-parameterized, and therefore the numerical optimization procedure is also harder. So this is like more a numerical problem. Okay, so how do we estimate this function? As I mentioned before, the message passing algorithm requires you to estimate the function that you use to compute the message sent to a node, the aggregation of all messages, and the update of your own embedding with the new message. And here we are actually not contributing anything, but we just look at attention network. So attention network transformers, they are very well suited for this task. And therefore, we essentially pass all this calibration to the message, to the transformers. So that's what we, and I think we all know transformers have been widely used in a number of neural network applications. Most recently, they are behind the most cutting-edge model of generative AI. And if we want to really see more how this procedure works, essentially we have a multi-head attention network. So the message from J to I in the layer L and 8 heads. So think about a head, one head, individual head, as producing its own version of the message. And this is basically the way that this version of the message is produced. Using some weights. So you weight the current embedding according to some weights, which is WQ, WK, WV. So these are all the weights. And then you aggregate across the attention heads by concatenating all these messages that have been produced by the different heads. And finally, you update the embedding of node I at layer L+1 using feed-forward neural network with some regularization technique. So this is essentially, I'm just showing you what a transformer does. Okay, so now let's go back to the problem in finance. So we want to find the best possible predictive model. And so far, basically, I've presented the GNN formulation, which takes firm characteristics and supply chain graph and uses it to estimate the stock return of firm I. So now we need to estimate this graph neural network. So what to do, we need to minimize the error, right? The error is basically defined as the square of the loss, the difference between the firm return, and this GI, which is essentially the predicted stock return. So theta is the vector of all parameters we need to calibrate using the attention network. XT is the vector of firm characteristic, and SGT is the supply chain graph that you observe at time t. You try to find a model that in sample fits the data better. And then basically we try to use it to estimate like the pricing error and also what's the out-of-sample Sharpe ratio of the portfolios that we can construct using this network. And I just want to make a point that this theta is not retrained for each firm I. We just estimate theta by looking at all firm I simultaneously. Otherwise, this would be extremely expensive, right? If you repeat this procedure for each separate firm. And what we do is just like take the graph, and for each firm, we look at the different graph because we look at the graph from the point of view of this firm. So we think about the target firm being 1, or target firm being node 2, target firm being node 3, and then we look at the graph of that D originating from that node. And then we construct this embedding, and we choose, we have to choose a dimension for the embedding, right? This HID, which is the final embedding obtained by aggregating all the firm characteristics. We compute it using a grid search, and we find that p equal to 40 is good, good size for the embedding. And essentially what this is capturing, all nonlinear pricing signal, including firm-specific features and supply chain interactions up to the hops. Okay, so then what we do, finally, we run a principal component analysis to extract time series variation in the embedding. So here we look at all the time, we look at the principal components across the entire panel, both firm, taking into account both firm, I, and both time. So this is like somewhat a panel principal component analysis. And this principal component analysis will tell us what are the top K directions if we focus on K components. So what are the factors, orthogonal factors, which captures most of the variation that we have in this data. And this variation is captured using a combination of supply chain and firm characteristics, right? Because remember that what we are doing is we are looking at these embeddings. So we are running a principal component analysis on the embeddings that we have constructed. So we want to see among all these embeddings that we have for each firm and for all times, can we find, let's say, a summary? Can we find a synthetic representation in terms of orthogonal factors, which are not capturing common information? They are all like capturing independent information. Finally, like to understand what's the role, how much they contribute to explain the out-of-sample Sharpe ratio, we construct long-short portfolios. So this is a very classical procedure in asset pricing. The idea is that you cannot really trade on these principal components, right? Because these principal components are basically linear combination of embeddings, which in turn are balance sheet, CompuStat type information. So this is not really tradable. But in order to develop something, to construct something tradable, we sort the firms into deciles based on their value of the principal component. And then we construct for each K, for each principal component, we construct long-short portfolio. That means that this portfolio, we will go long in the top decile. So we will go long in the firms which have a positive value for this principal component, and we will go short in the firms which have a negative value for this principal component, or which have a small value for this principal component. And then we look at the return of this portfolio, which is denoted by FTKLS. So this is the return of this long-short portfolio at time t, focusing on the principal component K. So that's, let's say, way to gain exposure to these non-tradable principal component factors. And then if we want to understand what's the role of, or what is the contribution coming from the supply chain factor, we regress out the principal components of the firm characteristics alone. So we basically look at, we regress the portfolio returns on the return of benchmark factors, DT, and we only focus on the contribution coming from the principal component, only contribution coming from the supply chain information, from the supply chain network. So essentially, this is ensuring that this procedure, this last step, is making sure that we have isolated the contribution coming from the benchmark factors, such as, for example, the Fama French factor, or the principal component of the firm characteristic alone. And therefore, what is left is just the contribution coming from the supply chain graph, right? Because the one coming from the characteristics alone has been already taken out, has been regressed out. Okay, so now let's see the this slide is just summarizing what the entire procedure. As I mentioned, we estimate the GNN network, then we construct these orthogonal principal components, then we construct long-short portfolio so that we can have something tradable and we can see how the out-of-sample Sharpe, how the Sharpe ratio of those portfolios looks like, and then we compute the asset pricing factor by regressing out the benchmark model, so the model where we only have firm characteristics. Okay, let me show the results. In the end, we have, again, this is just giving you an idea. These graphs are showing how the nodes and the linkages are over time. So we see that with time, we have more firms participating into the graph, and we have also more linkages. The dominant sector is the manufacturing sector, followed by the wholesale and real trade, followed by the electric and gas, and then mining and construction. You see that the number of nodes has been rising very heavily, steadily after like 1997. And nevertheless, the graph is rather sparse. You see that the average degree of the graph is between 0.4 and 1.6 across the years. That means that each node has one or at most two relations on average, right? So it's not really a very dense graph. And what we do is split the training versus data set in the edge space. So we want to ensure that the size of the sample set is similar to the, so the size of the training set is comparable with the size of the training set. And we find that 2006 is the year where we have an equivalent, we have more or less the same number of edges between the training period, which is 1977-2006, and the testing period, which is 2007-2023. So that's basically the rationale behind this choice. And then we look at performance metric.
Excuse me.
Yeah.
Hello.
Yeah.
So
I can hear you.
go back to the last page. I think it's you're seeing the nodes is just a dramatic increase for the manufacturing firms, right?
Yeah. You're right. This is
And
what we see in the graph.
Not much for yeah. So what does this exactly mean here? So there's much more collaboration that
no, it means that if you see the number of nodes, it means that these firms are, of course, doing a lot of business activity, right? They're reporting because each firm is required to disclose if they have, again, 10% of their sales to other customers. So that, of course, if you have more nodes, more manufacturing firm, that means that there is also more business relationship between these manufacturing firms and the other in the network. So that means that they are very active.
So let me put differently.
Yeah.
So would your pattern, would your result to be much more prominent among the manufacturing firms, or is this driven by the difference between the manufacturing firms and other firms? I'm curious to know.
Okay, so so you're asking whether how much of the result. So what's the contribution to asset pricing, for example, driven by the manufacturing versus the other firms, or is this a question? Or
right, exactly.
Yeah. So this, I mean, this would show up in the interpretability when you consider these factors coming from the supply chain graph. Then, for example, like if you interpret what this factor represents, if manufacturing is a large sector, then you should also have that these factors essentially can be interpreted, for example, as balance sheet information coming from the manufacturing sector. That's what you would expect.
Let me put this way.
Yeah.
Let me put this way. So, because I think you are going to have probably a challenge when you present to other people, then you'll still have no idea exactly what this is capturing. And so it'd be nice to do different stuff to show, identify further. For example, when I look at this, I would say, wow, manufacturing firms throughout years, and it's going to have much more increase of the connectivity, stuff like that, collaborations relative to other sectors. So maybe the return patterns will be either more prominent, or is it really driven by between the manufacturing and other firms? I think some of those kind of exercise would be quite meaningful to tease out the intuition of what you are capturing here.
Okay, thanks for the comment. Yeah, definitely. I think we can do more analysis in terms of understanding how the size or the component of the graph capturing by one sector is contributing to explain the returns. Definitely. Yeah, thanks for
because this is one of the things that people can capture, can understand. Wow, this is different. And so that connectivity seems to be changing all the time. So I think that's something worthy to be to drill more into it.
Yeah. No, it's a good comment. Thank you. Yeah, so just the interest of time, I want to show this. I mean, the performance metric, we're looking at the pricing error, which is essentially the average error computed as the difference between the predicted return and the actual returns. And then we look also at the cross-sectional average alpha, which is the average over the average over the firms of the time average of the pricing errors. So these are capturing essentially the average alpha is capturing basically the gains that you're making in terms of auto-sample sharp ratios. What's your alpha? How much basically alpha you're getting from using supply chain graph, and this instead the first metric is capturing more the pricing error. So again, first, if we ask what's the incremental value of the supply chain, this is what we find. Again, the pricing error. This is in sample and out of sample. And what you see, what is the main takeaway of this graph is that we find that having d equal to 6 turns out to be giving us the lowest RMSC or a maximum absolute pricing error out of sample. So that means that you don't want to have D which is too low, because otherwise you will have bias. You see that for D equal to 1, for example, you have a larger out of sample RMSC and also larger out of sample mean absolute pricing error. As D gets larger, you reduce the pricing error. And then, of course, if you look at larger D, you might actually increase again the pricing error, and this could be a manifestation of the variance. So that means this slide is basically showing that the bias variance trade-off that I mentioned earlier is reflected into the model, because you see that the best architecture is not looking at a very local subgraph or a very deep graph, but something in between. And finally, looking at the out-of-sample Sharpe ratio of those portfolios, these are the long-short portfolios that we have constructed by looking, as I mentioned before, by grouping firm into deciles, and also regressing out the firm characteristics alone, so that this is actually the out-of-sample Sharpe ratio contributed entirely by the supply chain graph. And if you look at the best model, like D equal to 6, which is the model that I showed earlier, where we had the best bias variance trade-off, we see that if you look at 5 factors, so this table has factors on the x-axis and number of layers of the network on the y-axis, you see that like if you only consider 5 factors, you are capturing 18% of the out-of-sample Sharpe ratio. If you consider like 40 factors, you go to 34%, right? So that's what I'm saying, that about half of the out-of-sample Sharpe ratio is being captured by only 5 factors. And the final question is, okay, what if we use supply chain data, but we don't use graph neural network? So in other words, what if we find a simpler linear model where we only look at the neighbor's firm characteristics? I mentioned like the focus of the earlier literature was more considering just the immediate neighbors of the node, and let's compute a weighted average of these characteristics. So you sum, essentially, it's a very simple average. You look at the firm characteristics of the neighbors of I, and you divide by the size of the neighborhood of I. And then what we do is to construct a benchmark, we consider like linear regression, like lasso and reach, just to have some regularization, where you regress Y, which is the firm return, on the characteristic of firm I and on this average X bar, which is aggregating all the characteristics of the neighbors of I, right? So that's what you do. And of course, this benchmark, we agree they use supply chain because you look at just neighbors of a node, but they don't use higher order supply chain relationships because you are stopping your analysis at the direct neighbors of a node. And this is the result that we get. If you now look at D equal to 6, again, that's the network that we are recommended because of the bias variance trade-off. We see if we look at 5 factors, like which is already capturing out of about 50% of the out-of-sample Sharpe ratio, we get an out-of-sample Sharpe ratio which is 0.18. And if you compare it with the benchmark using only direct neighbors, which is reach and lasso for the linear model, you see that this is 0.12 and 0.11. So the point is that we are able to capture additional Sharpe ratio compared to only focusing on the direct relationship of a node. And I think the reason is that we are picking up higher order relationship, which we are claiming to be significant in terms of improving your alpha, improving your out-of-sample Sharpe ratio. Yeah, just a final remark I wanted to make about interpretability. I think here interpretability means can we gain some information about which nodes, which network statistics are more important in this analysis. And what we do a Monte Carlo experiment. So the idea is that in order to assess the impact of a node in the analysis or in the predictability of returns, we do the following. We look at the firm I, and then we look at the prediction using the supply chain graph, SGT, and the prediction when we remove an edge from node I. So this G at I with SGTB means that we are looking at the supply chain graph on node I, but we are taking out at random one edge originating from node I. So essentially, if we do this randomly over, let's say, 100 Monte Carlo runs, then we could assess the sensitivity of the analysis with respect to a node. So for example, if we look at a node of degree 1, then for each group of degree 1 nodes, we take one edge from one of the nodes at random, and then we look at how much sensitive the procedure is to removal of an edge from a group of degree 1. So if we see that the sensitivity is large, for example, for group 1, for group 3, from a group with nodes of degree 3, it means that this group of degree 3 have more important, are more important in a way, or have a higher impact on the predictability of returns. And this is what we observe. So if we look at nodes of degree 6, larger than 6, you see that the sensitivity is larger, right? And especially if you look at within this group, you look at D126, which is our recommended architecture, you see that the average and standard deviation of the sensitivity of firms with degree larger than 6 is 41% and 40% higher than the sensitivity of firms of degree 1. So if you look at degree 1 nodes and D126 in this case, or any other D, you see that the sensitivity in terms of mean and standard deviation is way smaller than the one on nodes of degree 6, which basically contributes to making the point that the centrality of the firm, measured by this degree centrality, is actually one of the most important characteristics in returns, which means more central firms have a higher sensitivity. So that means that they are more relevant to predict returns. And yeah, that's it. I wanted to basically make the final point is that what we have done is propose the framework to extract these pricing factors from the supply chain graph by properly combining firm characteristics alone with supply chain graph information. And ideally, we also show that, I convince you that accounting for higher order relation in the network is important because it contributes to reduce the pricing error and also improve the alpha, or the auto sample Sharpe ratio of the portfolio. And definitely we get improvements over the Fama French 5 and other benchmark which do not account for supply chain graph. And it turns out that 5 factors can already capture half of the Sharpe ratio gain in these asset pricing tasks. Thank you. That's it.
So let me continue to ask several questions.
Yeah.
So I already, so my second question I'd like to ask is that basically, I think that it's interesting paper, and we are trying to get the best out of this, so to assess what is really mean. So I think some of the things will be helpful to make this more understandable.
Yeah.
One thing is when you talk about out of sample, I really wonder what's the stability of the so-called out of sample. So I just don't know, because whenever we have some kind of non-parametric stuff, we are worried about like overfitting, right? So some kind of stability of the performance would be nice. Let's say if you break the sample, let's say by half or whatever it is, like C or cycles patterns, whatever it is. So I think that could be useful to get a sense. Right now it's almost like a black box. It performs well according to certain metrics, but I think the stability of that metrics would be nice to show. That's one thing. Another suggestion is that it's really intuition. Now, since you are talking about you are really get something out of this the supply chain data relation stuff. So really people would ask, what is this stuff? And since you have this your model will decide the weights it put into stuff. So I would imagine those weights, because after, so you actually have those weights, you have the data. So some analysis of those weights or some other features, the model determined features, their relation with the performance would be nice, or with the firm characteristic would be nice. Actually, that'd be extremely interesting, because it kind of showing, wow, it is emphasizing this kind of relation. And this kind of relation is representing, it's some combination of some firm characteristics, stuff like that. I think that would be very meaningful to help. Now, another comment is that I think people would also like to know, because when we know the intuition, if we understand better of intuition, people would be curious to know how the improvement of the AI right now, all the I don't know, the reasoning models, stuff like that, how will the future would they make this even better, whatever it is. My final comment or question is, I would think this kind of graph, the relationship stuff, supply chain would be useful in the global trade or whatever literature, global supply chain. And right now, I think one of the problem of the Trump administration is that it really underestimates the sophistication of the global supply chain. So if you have something kind of to show, it's complicated, it takes time to move, it's related. And so if you do some kind of one-shot measure, it's going to hurt the thing. That would be, to me, it's even more interesting than factor models. So some of the comments, but thank you for helping me to think about those issues.
Yeah, no, these are like great points. Like in terms of the first point that you mentioned, I will just briefly respond because we haven't done some of the analysis that you suggested. I mean, for example, understanding the weights, how the weights of the calibrated model reflect the contribution coming from different sectors. I think we are thinking about adding this in terms of just measuring over time. While if some sectors are contributing more than others, of course, this requires some way of summarizing or making this information representable in a more compact manner. But definitely it's manageable. In terms of the last point you made, I think this is very interesting, looking at the global trade network. And you're saying, instead of looking at the implication on asset prices, just understanding what are the implications maybe from macroeconomic risks coming from blocking some relationships in the supply chain graph. So comparing, that would be a separate study, but I think one could still use these machine learning methodologies to do that. Yeah.
Right. Yeah.
But these are all great questions. Thanks for bringing up these points.
Oh, great. Are there any other comments or questions? So please feel free to unmute yourself if you have any questions or comments. So if there are not any additional comments or questions, as we are running out of time almost, I'd like to thank Professor Capponi for your presentation today, and also for the engaging discussion comments. Yeah, if you have any other comments or questions, I think it could be great to just email Professor Capponi to further communication. Okay.
Right.
Yeah. So before concluding today's session, I'd like to share that our upcoming webinar would be on 23rd of April, which is about the fintech and the Web3 techniques. So if you are interested in the Web3 and fintech, so you are very welcome to join our next webinar on 23rd of April. Yeah. Okay, thank you, Professor Capponi. Yeah, and
Thank you
also
so much.
thank you all the audience once again for your participation today. Yeah, we are looking forward to see you all in our next webinar. Okay.
Perfect.
Yeah.
Thank you so much, Yvain. Thanks everybody for questions, for coming, and the participation. Thank you.
Okay.
Thank
Thank
you.
you all. Yeah.
Thank you.
Have a
Bye.
great day.
Bye.
Yeah. Bye.